When real-world observations cannot be approximated using a straight line, we resort to nonlinear regression. Nonlinear regression is the process of fitting a nonlinear equation to data. In this course, we'll be looking at using exponential and logarithmic models to describe a dataset. Exponential regression is used to model situations where growth begins slowly and then rapidly accelerates without bound, or when decay begins rapidly and then slows down and approaches zero. The general exponential equation is f at t is equal to a naught times e to the kt. Recall this from Model 6. So here we have a requirement that a naught must be greater than 0. And remember, a naught is your initial value, so the value of your function when t is equal to 0. And the exponential function is increasing, so it's experiencing growth when k is greater than 0, and it's decreasing or decaying when k is less than 0. Now let's look at an example that requires exponential regression. In 2007, a university study was published investigating the crash risk of alcohol-impaired driving. Data from 2,871 crashes were used to measure the association of a person's blood alcohol level, BAC, with the risk of being in an accident. The table below shows the results from the study. The relative risk is a measure of how many more times likely a person is to crash. So for example, a person with a blood alcohol level of 0.09 is 3.54 times as likely to crash as a person who has not been drinking alcohol. So here we have our independent variable of the blood alcohol level, and the relative risk of crashing is your dependent variable. So we let x represent the level, the alcohol level, and y represent the corresponding relative risk. And we want to use exponential regression to fit a model to this data. First, we're going to use Excel to create a scatter plot. First, take care in entering all of your data into Excel, then highlight the given data, and you can insert a recommended chart, so the scatter plot. And here we get an initial idea of what our data looks like graphically. First, we can put some titles in, so our chart title as well as axis titles. Observing this scatter plot, we can see that it does not appear to follow a linear trend. It appears to be exponential. Therefore, we should try modeling it with an exponential function. To do so in Excel, we right-click on the dataset and select Add Trendline. And when our options appear, we're able to select the type of trendline option. So we can select exponential and display its equation on the chart. And we find that we have an exponential function with a base e to describe the data set. We can see it does a very good job of approximating the data set, especially on the domain. Now, using the equation from Excel, we can make predictions. So let's note the equation here. Y is equal to 0.583 times e to the 23.818x, where x is the blood alcohol level and y is the risk of crashing. Now we would like to make a prediction. So after 6 drinks, a person weighing 160 pounds will have a BAC of about 0.16. How many times more likely is a person with this weight to crash if they drive home after having a 6-pack of beer? And we want to round our answer to the nearest hundredth. So in terms of our equation, we would like to find the relative risk, which is y, for x is equal to 0.16. And we can solve for this by subbing it into the initial equation. Now, if you're evaluating this on your calculator, you want to make sure that the entire exponent is raised with a base e, and we get 26.35 when rounded to the nearest hundredth. It's always a good idea to confirm that this seems reasonable based on our graph, and we can see if we have a blood alcohol level of 0.16, that does seem as though that would be over 20, and 26 seems quite reasonable. Therefore, a person that is 160 pounds is 26.3 times more likely to have a crash in their vehicle if they drink a six-pack of beer than if they do not. Now we're going to look at logarithmic regression. Logarithmic regression is used to model situations where growth or decay initially accelerate rapidly and then slow over time. The logarithmic equation is generalized by f at t is equal to a plus b times ln of t. Remember that ln is your base e logarithm. Here we know that t must be greater than 0, and our logarithmic function is increasing when b is greater than 0 and decreasing when b is less than 0. And we know that a is our initial value and b cannot equal 0 because it won't be a logarithmic function. Let's look at an example that requires logarithmic regression. Sales of a video game released in the year 2000 took off at first, but then steadily slowed as time moved on. The table shows that the number of games sold in thousands for the years from 2000 to 2010. We're going to let x represent the time in years, starting with x equals 1 for the year 2000, and y represent the number of games sold in thousands. Use the logarithmic regression to fit the model to these data points. So first we're going to create a scatter plot in Excel. We're going to describe the relationship between the two variables, and then add a trend line to model the relationship. Putting the data into Excel, remember that we defined x as being the years, starting with x equals 1 for the year 2000. So we need to replace, instead of using the actual year, we define values of x to represent these years. Okay, now we can create a scatter plot. And we can see that the increase in our y value initially goes up quickly and then levels out. And this could be described using logarithmic regression. We can now add a trend line, which is the same process as when we were creating linear regression, and change the type to logarithmic and display the equation on the graph. Now we can see our a value and b value and use this equation to make predictions. Depending on what we're interested in learning and doing, we may just use a quick graph like this to come up with the scatter plot, describe the trend, and add a trend line to gain its equation. But if we're wanting to use this for a more professional purpose, we should add a chart title as well as axes titles and format it according to any requirements for work or education submissions. For the purpose of this lab, we're just looking to, we don't want to submit anything with titles, we just want the equation. So we know that y is equal to 10 0.454 ln of x plus 141.91. So if games continue to sell at the rate predicted by the model, how many games would be predicted to sell in the year 2020? We want to round to the nearest thousand. Recall that the year 2020 translates into x is equal to 21. So we're looking for the value of y when x is equal to 21. We find that our prediction would be 173.737436. Therefore, we could assume that if our model is accurate and is maintained to the year 2021, that we would expect for there to be approximately 174,000 video games sold. Since we're predicting way outside of our data, this is considered an example of extrapolation, and you'd want to do some research on the topic of video games and video game sales, as well as look at what would be reasonable to know whether or not the model would hold this far out. So I hope you found this unit helpful. Don't forget about your Excel assignment on regression that is due according to the deadlines on D2L. Good luck, and let me know if you have any questions.